Today, we're going to look at the effect of gravitation within the universe. And we'll take as a starting point 28 billion galaxies with a typical mass of 2.2 times 10 to the 42 kilograms. This is typical of the Milky Way or the Andromeda galaxy. And we take the total mass of these galaxies then is 56 times 10 to the power 51 kilograms. Now, we know from the Einstein equations of general relativity that there is a Schwarzschild solution, which means that if you have sufficient mass within a radius r, then an event horizon will form. And for this mass, that event horizon will be at 8.77 billion light years. Now, space is curved so that nothing can cross the event horizon. The reason for these figures, for the position of the event horizon, will become clear later. So here's an illustration. We have a finite universe. This is the event horizon. And these galaxies, these 28 billion galaxies within the event horizon, result in the formation of the event horizon at this distance. Now you have to think of the expansion of space, and the expansion of space is moving all the galaxies away from the center of the universe, but with the event horizon in place, the galaxies cannot cross the event horizon. So what happens is that over time, there's a buildup of galaxies just this side of the event horizon. Space itself, the medium of space, is expanding and effectively crossing the event horizon, because the event horizon is a boundary in space which remains fixed because the mass within the boundary remains fixed. So these galaxies will be radiating energy, and that radiation will be detected, and by the time it reaches the point of observation, the radiation cools to around 2.7 degrees Kelvin, and that is what we observe as the cosmic microwave background. And because of the expansion of space in this region, it takes 13.8 billion years for the radiation from that distance to cross 8.77 billion light years. And that's the explanation for this figure, because we know that the cosmic microwave background radiation is coming from a look-back time of 13.8 billion years. And this is a plot of the cosmic microwave background radiation, showing subtle variations in the radiation at different places in the sky. And you can see this looks not unlike a galaxy field. In fact, the cosmic microwave background looks very uniform if we just treat it as 2.728 degrees Kelvin, and it's only variations at 1,000th of a degree that we see this anisotropic variation, and it's only at variations of 1/1,000,000th of a degree that we see the detail of the variation that was shown in the previous slide. And this middle figure here is interesting because this is the cause of this is attributed to the fact that the Milky Way is moving relative to the CMB rest frame, and it's moving at a speed of around 552 kilometers per second, and that is why one region appears hotter and another region appears colder. And we explain that because the Milky Way, as we shall see, is positioned. We can use the anisotropy to calculate the position of the Milky Way in this figure. So it's moving at 552 kilometers per second relative to the cosmic microwave background radiation, which is coming from all directions uniformly. And for that to be the case, the Milky Way must be around 26 million light years from the center of the universe, from the center of the galaxy distribution, and from the center of the event horizon. And it's that position, relatively close to the center of the universe, that gives us the point of observation that we have. So again, being quite close to the center of the universe, the galaxies are moving away from the center due to the expansion of space, but as the galaxies approach the event horizon, there is a gravitational effect which reverses the direction. It reduces the velocity in the radial direction. So that these distant galaxies, although they're still being moved out by the expansion of space, are being accelerated towards the center. Excuse me. So the existence of 28 billion galaxies within a radius of 8.77 billion light years will cause an event horizon. Galaxies are held at the event horizon even though space is expanding. And radiation from just inside the event horizon takes 13.8 billion years to reach our point of observation because of the expansion of space. Given that the velocity of the Milky Way, as observed, is 552 kilometers per second, relative to the cosmic microwave background rest frame, we can calculate that the Milky Way galaxy is around 26 million light years from the center of the universe.